I would like to give the word to Jonathan, our lead engineer.
Hi, thanks, Rens. I would like to explain a bit more about the active learning part. Rens touched this topic a bit, but I would like to explain it a bit more in detail. Then you get some feeling of what happens in the background, I think this answers also a couple of the questions asked before. So if you're not familiar with active learning is something that's more or less in between supervised learning and unsupervised learning. Both types of learning are very popular in machine learning. With supervised learning, you do have a training data set, and you try to predict based on a trained model what you trained on this little data set, and then you predict on a second data set or a part of the first data set which was not used for training. And then you do have unsupervised learning, where you just put the algorithms in there and just see what happens. But active learning is where you actually interact with the model. And to explain this, we are usually displaying this active learning cycle. And I call this with our team human in the loop, because this is also known as human in the loop AI. But it's actually active learning. And what happens is that there's a pool on the right. And the pool on the right is actually your data set with all the publications. So in most of the examples, for example, 5,000 papers are in the pool when you start. What you would like to do is you would like to present very interesting papers to the annotator. In our situation, we are presenting the most probable papers to be relevant to the human researcher. And the human researcher labels this data set. Now, as you know, the model is not perfect, especially not in the beginning, because we start with very little information. So in the beginning, you have to direct the model pretty much. So on the left, you see the labeled data set, the labeled data. This is the output of what the annotator has labeled. The labeled data, in our situation, we label one by one, but you see in this picture, you see 3. So you do have a little set which you label, and then, yeah, some are relevant, some are irrelevant, and you put them back into the model. The model is retrained, and the model is applied again to the pool. And for every item in the pool, we do have some sort of score, some score of relevance. If a paper is relevant according to us, then we put it back to the human researcher, and so on. We keep going with this cycle. Normally or usually, active learning is focused on training a nice model, such that you can use that model later on to predict the outcome of other values in a different data set. So for example, you see this a lot with image classification. It's very complicated to make a training data set for image classification, because you need to label so many of these images before having a nice model. So what they usually do is they are using active learning, such that they can tweak the model very specifically for the errors that are made for the model, and then the result of this process is an unbiased, hopefully unbiased trained model. We see this problem a bit different, so we call this researcher in the loop. And in our situation, the output is not the model, but the output is a bunch of systematically reviewed publications. Why this is different from what we've seen in the previous slide is that we can actually train our model in such a way that it's not perfect for generalization, We can make a very skewed model, but if we get all the publications relevant to us, it doesn't matter. So we are more focused on training towards finding all these relevant papers than building a nice model. And this is slightly different of what we have seen in the active learning literature. There's work on this, definitely, but we try to push the most out of it. And Gerbrich would like to show you later on the simulation results of this, and they are very promising. It's very important to us that this entire process has some systematic structure. We would like to see all the publications. It should be done with the same inclusion criteria like Jan told us before. So this is very important to us. This is less important in the normal active learning cycles you see. I think this gives a short introduction on how active learning works and how our engine works. I would like to show also our GitHub page. I will share my screen to give you some sort of overview of what we're actually doing, because this cycle seems to be very simplistic. There are only a couple of interesting components, but this results in a code base which is growing on a daily basis, and it's getting bigger and bigger. We are working on GitHub. So GitHub is an open source coding platform, a social coding platform where you can host your projects. We do have an organization over there named ASReview with all the projects we are actually working on. Our main project is the ASReview project. This is the base of all the code in the actual software we are shipping to our users. So yeah, there's clear documentation on this page and examples where you can start. We do have a nice quick tour. So we are always focusing on documentation because it's very important that users are actually able to use the software and not stuck in the beginning. So this is our quick tour. I would like to point you to this quick tour. I think Rens will share the link in the meeting chat. Where you see what actually happens step by step, and that gives you a bit more feeling of what you can do with our software. For example, there was one question on what can you import? Can you use your own datasets? Yes, you can use from file, you can use from URL, you can use one of the datasets in our plugin, or we even do have examples. These examples can be used to show you that our software actually works. This is very interesting. There's also documentation on this. So if you would like to give it a try and you're not convinced after this talk, which is a bit sad, by the way, Rens is very convincing always, but you can give it a try yourself and see what happens if you do this yourself. What Rens mentioned before is that there are plenty of side projects, and one of these side projects is that we are working on a collection of data sets which we can benchmark. So we do have a couple of interesting data sets fully labeled. And these data sets can be put in our simulation mode. And the results of these simulations are seen in the presentation by Gerbrich in a minute. So for us, it's very important to find those data sets. And although it seems quite obvious to collect those data sets, fully labeled data sets, this is important to us. It's not that obvious. Unfortunately, not everyone is sharing those data sets when they publish the paper. They are always sharing the end result, but not the entire label process. So we are labeling this with zeros and ones. So a 0 is exclusion, a 1 is inclusion. We are actually looking for more of these data sets, also in different domains, because what Rens told before is that there can be a huge difference in the domain. So if you are working on systematic reviews and you do have fully labeled data sets, please drop a message on our GitHub page or send us an email. We are pretty much interested to put your data sets in our simulation software, or you can give it a try yourself. And then see what happens. What happens in your domain if you automate the process of systematic reviewing. Yeah, we do have a couple of plugins, and these are also interesting. We do have, for example, a plugin for the COVID-19 situation. In this plugin, we are making a lot of datasets available relevant to COVID-19, such that you do not have to compose them yourself like Jan did before.
Okay, Jonathan, I'm going to take over the screen again so that you can finish your...
Yeah, that's perfect. So the last project we have is the simulation project, but it might be interesting if Gerbrich tells us more about this. Yeah? Gerbrich, the floor is yours.
Thank you, Jonathan. Well, I've performed several simulation studies with the ASReview software, and for that I used 6 data sets from the repository Jonathan just showed you. And I did this to get a better idea of the performance of our software. And more specifically, there are all kinds of options in the software, which Arjan already mentioned in the questions. So I'm glad you asked, Arjan, thank you. So I also wanted to compare some different models within ASReview to see what the potential performance of our software is. Can we go back one slide? Then I have still, thanks. So I used 6 existing systematic reviews for my simulations, and they all have varying number of studies, several thousands in there. And as you can see on the plot on the left, only a very small part of the candidate studies is relevant to a systematic review. That's the tiny green spot you see in there. So these researchers, they have manually screened these papers, and my goal was to figure out how much time we could have saved if we had used ASReview. So next slide, please. So ASReview currently offers the option to select a machine learning model when you start screening. That is naive Bayes, support vector machine, logistic regression, and random forest. And those are 4 models I compared. And I also compared 2 different feature extraction strategies, which is the way how you represent the text of the abstracts in your model. And all models that I used, they adopt the same query strategy, which means they presented the most relevant abstract first. And the way the training data set was rebalanced every time after labeling was also constant across models. Next slide, please. So in the end, I ended up with 7 different models, which I all simulated on the 6 data sets. Every simulation started with 1 prior inclusion and 1 prior exclusion, which means we had 2 publications to start with. And what you see here are the results on the PTSD data set. I will take a minute to explain what this plot shows us. So on the x-axis, you see the proportion of papers in your data set that you have screened. And the y-axis displays the proportion of relevant publications you have found. Then the diagonal black line, the striped line, that displays the the rate of finding relevant publications we'd expect if you were screening the data set at random. And then the colored lines, they display the behavior of our models. So as you can see, they are way steeper and way higher than screening at random. Then the vertical lines, they display the point when your model finds 95% of relevant papers. And as you can see, the best performing models on these data sets, they found already 95% of the relevant publications after screening less than 5% of the data set. And in this case, that means that after screening only 300 of 6,000 publications, we've already found more than 35 of the 38 relevant papers. So that is quite impressive. So, well, at least for this data set, the model does much better than when we would screen at the traditional style. Now, for this data set, it works very well, but for the other data sets, luckily, it was also very well. For the remaining data sets, we see a bit different results. They are not all as great as the PTSD data set, but they still perform much better than screening at random. And some interesting patterns I see here is that all the 7 models I simulated, the ordering is sometimes a bit different, but it's fairly similar across the data sets. But well, the large difference is actually not between the models. Rens? Rens, do you want to say something, or you're raising your hand? Or I cannot hear you.
No, please continue.
Oh, can you go back to the next slide then? Sorry, I thought you want to say something. But the biggest difference is not between the models, but it's between the data sets. And you see that for some data sets, ASReview still does quite a good job, but it's not as great. So you still have to screen maybe 30% of the publications instead of 5%. And then we can go to the next slide, because we now know that, well, for all the data sets I simulated, the ASReview models work pretty well. And what we would like to know next, and that relates to the question that Arjan asked, is what makes then that sometimes a model does very well and sometimes it does a bit worse? And how can we advise researchers to pick a model for their data set? So it's I think it's the question of generalizability to different data sets is what I want to work on next. But I think the biggest conclusion is that, well, you could safely use ASReview on a data set, and it will at least perform better than at random, and much better actually. So for my simulations, it was, well, screening maybe maximum 40% of publications, and you find almost everything. So we were very happy with those results. And how much time do I have left?
Take 1 minute or so.
All right. So another question that I'm working on is how to tune a model for new and unseen data sets. So for this data sets, they were already labeled, and I tuned the models and the hyperparameters to perform well on those data sets. So we are looking at a maximum performance scenario at the moment. But the biggest question is how to tune a model for unseen data sets. So here you see a random search for the optimal hyperparameters I performed on my for every data set individually. And if we now go to the next slide, you can see this is the same plot as the previous one, but I ordered the trials of descending loss. And now what I would like to do is some sort of validation. If you go to the next slide, on for optimizing hyperparameters for data sets that are not the same as the data set that perform the simulation on. And this is actually very like a new project. So if anyone has interesting input on this, I would really like to hear. And to close this presentation, I would like to mention again that if you have your own data, you can also perform these simulations yourself. So the figures and everything, the ASReview has a simulation mode, and yeah, go ahead and see if it works for your data as well.
Okay, cool, Gerbrich. Thank you so much. And I already see some people in the chat willing to share data, so we will definitely contact you.
Nice.
Thanks, Gerbrich. The next presentation is by Raoul.
Hello. So a few days ago, Rens asked me if I want to do a presentation about this subject, and I said no, because it was too experimental. So instead what I did is to work yesterday and wrote a few hundred lines of code and actually tried to make some results. So it's all very experimental, fresh from the press. And yeah, you can go next. And hopefully there will be at least some interest. So the question I'm trying to answer is, when should a reviewer stop? Because so far we have seen that the classification and the active learning process is very efficient, because it will show you relevant references first. But then the question is, like, when do you finish your review? Like when you learn the ASReview tool. Because, for example, you can see on the right the picture that at 7% of the after reviewing 7% of the papers, you've already seen everything except one. But how do you know that there's still one left? And even after 12%, like, we know, because we had the whole review was done, that everything was found, all inclusions were found. But how do we know this? And the problem is really, like, from a statistical point of view, it's very hard, because the two populations of the reviewed papers and the non-reviewed papers are from a different population. So you can't just, like, extrapolate from the reviewed one to the non-reviewed one. And even if you have a better classifier, like the better your active learning process is, the harder it is to estimate the other population, because the populations will be even more different. And ideally, we would like to know if we're finished without doing any extra work for the reviewer. Like, it's like, ideally only the computer has to do some calculations to know if we're done. Okay, next. So I read a paper on the Fast Read 2 project, and they're doing something similar to us, but they describe an algorithm, and I didn't actually do the algorithm itself, but what they use is to use the probabilities from the classifier, and assume that there is some information in this classifier, in the probabilities that are output by this classifier. And so this information would be, for example, that papers that match your question better would have a higher probability than ones that also match but are less relevant, so even though they would be included. And using this and the second thing I assume is that systematic reviews have some similarity to each other. So they have some common structure among them, and you can see on the right, I don't have the time, unfortunately, to explain how it actually technically works, but you have some distribution of papers, of inclusions, and the shape is similar to between different reviews. Okay, next. So this black box algorithm that I didn't describe. So how does it perform? So I use the PTSD dataset to see the estimate versus the actual found inclusion. You can see on the right. So you can see that the estimate is a little too high. It starts out a little too high, because ideally your estimate should be like a straight line, right? You would estimate your perfect estimate that you always find 38 inclusions. But it's a little bit too high, but at least it seems reasonable. So for the simulation, I did 10 simulations, and for each of these simulations, I computed the error at every time step, or at every 100 papers. Okay, so next. Okay, so now I did it on another dataset, because it's always good to do your simulations on a few different datasets to know you're not biased by just having one lucky run. So I did also use the Wilson dataset. I used the same procedure, but now I actually look at how if there's a bias or if there's a variance, because there's a variance between the 10 different simulations where you have different inclusions at different time steps. And then also I compared it to sampling extra 50 random papers. And you can see that actually for the random papers, of course, there's no bias, but there's a high variance, because it's hard to, if you have one inclusion, then it will blow up in your estimate. So you can either have 1 or 0, and for the other one, it has a lower bias, but our algorithm has a higher bias, but a lower variance. So it's always a trade-off. And I think that we should probably go to questions. The next slide is not so important, so let's just skip it and go to questions from my part. Thank you.
Okay, Raoul, thank you so much. And yes, this is experimental work, but it's maybe the question in active learning, right? Daniel? Daniel is also here.
Hi, I'm here.
Yes. So, what do you think about this? Because these results are also new for you.
Yes. Thanks, Hans. Yeah, so I was asked to give a short reflection on maybe the future of this whole endeavor. And I would also like to give a short reflection about where our work stands within the broader field. So we are not the first group to come up with the idea of using machine learning to help the screening process in systematic reviews. There's been some work on it previously, only a subset of that work using active learning, but there is a subset of that work that tries to do that. But it's very difficult in general we found that it's very difficult in general to understand to the extent to which different systems work across a broad range of different topics. And that's why we've been trying to evaluate on a lot of different data sets, and as you've seen, and trying to get more all the time. So I see that Ciara Keenan from Cochrane Ireland is offering some data. That type of thing is super welcome also for us to verify whether our system works across more than just a biomedical topic or just a social science topic, for instance. Like Rens is saying, one of the frontiers in active learning generally actually is to estimate the error rate that's still left over. And it's a challenging problem, and we're still working on it. And it's a challenging, this whole task is a challenging machine learning problem in general, because there are so few inclusions generally in systematic reviews. But a very small improvement in prediction can really yield a large benefit in number of papers that one doesn't need to read. So in future, I think that this is what Raoul presented, this working more on this research question is one of the things that we really like to look into, and also to create a more large-scale objective benchmark to see how all the different systems that have been devised over the years compare with each other, including our own. So I think that's what I wanted to say, Rens, but maybe there's some room for a few questions. I see we have 3 minutes left.
Yeah, so is there someone with a very urgent question? Well, and if you have questions, yeah, I see a question. Please.
Hi, thanks for the nice talk. So I was just wondering, so I actually don't understand like how the features of the abstract, like how all of the papers or how all of the reviews are described in terms of the machine learning modeling. But can you also maybe can we also try to do this via a recommendation engine sort of approach? Or has this been tried, or?
So I think I can answer that, and Jonathan can also provide more detail. So first of all nothing we do is secret, right? Everything is on the GitHub. You can scroll through the code and see exactly how everything works. And there's no other code that we have lying around somewhere. That's what you see there is really what you get. That's really what we are using. So that's first off. We have different representations in terms of the representation of the titles and abstracts. So text representations, we used different ones, which you can also see in the code. So we have a simple representation, TF-IDF, and then we have progressively more complex representations, embeddings, and neural nets as well that we experimented with. Sorry, what was the second part of your question?
On the recommender systems.
Recommender systems, yeah. So recommender systems are are not fundamentally different from the task that we present here. Of course, recommender systems are a field that's developed a little bit in parallel to classical machine learning, like classical classification, for example. But over the years, they've grown very close together because people realized these tasks were overlapping, and that's the case here as well. In a way, you could represent this as saying that you recommend people a paper based on their previous choices. And the way we implement that is using a classifier. And that's a well-known phenomenon in the recommender system literature that these tasks are basically interchangeable.
Okay, thank you, Daniel. Given the time, and I know there are many more questions, do not hesitate to contact us via GitHub or email